I've seen countless teams build these incredibly fast cars that, well, never actually finish a race, and they all make the same fundamental mistake. So today, we're going to do a strategic deep dive into the one discipline that truly separates the champions from the cars that end up dead on the track: functional safety. Let's just start with a number: 40%. At major competitions like Formula Student Germany, our data shows that up to 40% of all electric teams fail to finish. Think about that. That's nearly half the grid scoring 0 points in the dynamic events, not because they were slow, but because their car just stopped. So what's really going on here? This isn't about a lack of engineering talent, and it's certainly not a shortage of horsepower. The real question, the one every team captain needs to be asking, is what is the root cause of these catastrophic race-ending failures? Well, here's the fundamental strategic error. It's a singular, almost obsessive focus on maximizing raw power. Teams pour months into shaving a few grams here, adding a few kilowatts there, all while completely ignoring the absolute foundation of all on-track performance: reliability. So let's be perfectly clear about this. A car that finishes a race is infinitely faster than one that doesn't. We have to reframe functional safety. It's not some boring rulebook you have to comply with. It's your primary competitive weapon. It's the engineering discipline that gives you the confidence to push your car to its absolute limit. Okay, let's break down how we're going to build that confidence. So here's our briefing plan for today. We'll start with the framework, and then we're going to dive deep into 3 critical technical battlegrounds: noise, heat, and water. Then we'll wrap up with an action plan you can literally start tomorrow. All right, first step. Let's really cement this core idea. A world-class safety architecture isn't about slowing your car down. No way. It's about building a system so robust, so trustworthy, that you can confidently push your powertrain to its absolute thermal and electrical limits, lap after lap after lap. That is what performance really is. Now, to build this kind of foundation, you can't just be reactive. You need a structured, professional engineering framework. So we're going to focus on 5 absolutely critical pillars of powertrain design. These are the 5 pillars of functional safety. Seriously, think of them as the foundation of your house. If any one of them is weak, the entire structure is going to collapse under pressure. Mastering each one of these is completely non-negotiable if you want to build a car that isn't just fast, but is resilient enough to actually win. Okay, let's get into the details on 3 of the most critical areas. So your inverter, the heart of your powertrain, it creates a complete hurricane of high-frequency electrical noise. Your first, and maybe your most difficult challenge, is making sure that your most critical safety sensor, the insulation monitoring device, or IMD, can think clearly inside that electrical storm. Now, if this electrical noise from the inverter fools your IMD into thinking there's a real safety fault when there isn't one, it triggers an immediate shutdown. And just like that, your race is over. The key, the absolute key, is to correctly filter the signal coming from the Bender IR155 so your vehicle control unit, your VCU, can understand its very specific and kind of weird language. And what's really interesting here is how this IMD communicates. It doesn't use a modern CAN bus signal. No, it uses a simple PWM signal at different frequencies. Your VCU has to be smart enough to perfectly distinguish the 10 Hz everything's fine signal from the 40 or 50 Hz shut it all down now signals. And it has to do this while kilohertz level noise from the inverter is literally screaming in its ear, trying to confuse it. This is where robust hardware and really smart software filtering become absolutely critical. Okay, next up, heat. In the endurance event, heat is your #1 enemy, period. The rules are crystal clear. If any single battery cell hits 60 degrees Celsius, you are out of the race. Done. A simple strategy of just shutting down the car at 59.9 degrees, that's a complete failure of engineering strategy. The winning strategy is active thermal management. We call it torque derating. See, instead of waiting to fall off that cliff, you intelligently and proactively limit the motor's power output just enough to keep your battery temps in a safe, optimal window. You stay on the track, and you'll keep scoring points. But how you implement this is absolutely crucial. And this slide just illustrates the 2 main approaches perfectly. A lot of teams try to use a PID controller, but honestly, it's incredibly risky. Because of thermal inertia in the battery pack, a PID can easily overshoot your target, hit that 60-degree hard limit, and bam, shut down. The professional deterministic solution is a simple lookup table.
It guarantees predictable control, ensuring you extract the absolute maximum performance from your battery without ever risking a thermal shutdown. It's the smart plan. So you could have the most brilliantly engineered car in the world, but it is utterly useless if it can't pass technical inspection. And for electric teams, the rain test, well, that's where so many dreams are washed away before they even get to the track.
Passing this test isn't about luck. It's about meticulous, almost obsessive attention to detail. This isn't just a list of parts. This is your survival checklist. Every single one of these items matters. Forgetting something as simple and cheap as a 10-cent sealing plug for an unused hole in a connector can, and I promise you, it will, end your entire competition.
Okay, we've covered the core strategy that safety is what enables speed, and we've dug into the critical details of noise, heat, and water. So the big question now is, where do you start tomorrow morning?
Here is your 3-point action plan. First, get your critical long lead time hardware procured now. Don't wait. Second, prototype your most critical safety circuits. I'm talking about the Brake System Plausibility Device, or BSPD. Prove that the logic works on a simple breadboard before you ever even think about designing a PCB. And finally, launch your failure mode and effects analysis, your FMEA. Start the document today. These steps right here build the foundation for everything we've talked about.
So I'll leave you with this one question to take back and discuss with your team. Because in the world of Formula Student, the simple, hard truth is that the car that finishes is always the fastest. Thank you.